ถึงไม่รู้ไปหรือเปล่าไปไม่เลยแดงเลยเหรอโอ้ my god แดงเลยเหรอเกิดอะไรขึ้นไม่ไปเลยไม่ไปสักนิดเลย 338 we used it this one instead ก็ไม่ไปอยู่ดี I don't know why มันก็ต้องอันนี้ไปอันนี้ alright no but yeah we have the virtual camera like this วาลินครับวาลิน no yes sir this one this one meeting eyeliner email นี่ครับนี่ไม่765แล้วก็ C to let's see let's see what's going on yeah soon to YouTube alright so good มีอะไรสีแดงด้วยไม่น่ามีนะSo good afternoon, everybody. Welcome you to SCI33205 มีพีรทัศน์เข้ามาไม่มีใช่ไหมตรงนั้นyeah welcome you to SCI33205 physics number 4 this is 4 section for the class M605 right and yeah so 3 people นะครับที่ Zoom ก็ที่ YouTube นะครับก็ไลฟ์ไปให้นะครับคุณเปิดหาเองนะครับหรือว่าจะให้ผมส่งให้เพราะว่ามันได้YouTube ไม่ได้เปิดไลน์คุณ เปิดไลน์ก่อนไลน์อยู่ไหนสำหรับคนที่จะดูที่YouTube นะครับครับแล้วก็สัปดาห์หน้าครับวันพุธถ้าใครสนใจอยากเข้าเรียนวันพุธสัปดาห์หน้าเรายังย้ายมาพฤหัสอยู่ครับจะมีสัปดาห์ครับwhat else yeah the ส่งลิงก์ที่ YouTube ให้นะครับถ้าใครอยากดูที่ YouTube นะครับสัปดาห์หน้าครับถ้าใครอยากเรียนร่วมกับม.6 สาธิตองคลักษณ์นะครับแต่ว่าเขาก็เหมือนคุณนะครับไม่มีการตอบอะไรเท่าไหร่ครับก็อยู่นิ่งๆของเขานะครับโอเคครับก็จะประมาณนั้นนะครับก็สามารถเข้าได้นะครับเวลาเดิมของคุณนั่นแหละครับแต่ว่าหลีกให้เขา3 สัปดาห์เนื่องจากว่ามหาวิทยาลัยขอผมไว้ตั้งนานแล้วผมก็เลี่ยงปฏิเสธครับปรากฏว่ามีปัญหานิดหน่อยนะครับก็เลยต้องเข้าไปสอนอีกให้เขานะครับเพราะว่าปีที่แล้วผมรับมาตลอดนะครับ Alright, now let's talk about our stories in okay, most of you let's remind again we สุภวิทย์พัสิทธิ์นะครับพฤตินันณัฐวินธนกรกรนะปฏิหารวชิรวิทย์นะปนธรวาลินปีรทัศน์ปฏิหารภาวัฒนนทกรภวิทย์นะครับokay now let's talk about I think I have recorded already right yeah let's talk about our stories for M605 right here we arrive at almost at the end of this chapter this one okay let's remind ourselves the let's remind ourselves we this all right who else nothing more yeah the next topic we will talk about is the determination of induced currents and so on in yeah and after that after we consider several cases for the induced current determination we will have 3 or 4 examples okay a couple of examples and in the oh no กดผิดนะครับไปอยู่ใกล้กันด้วยin those example we need to use this formula okay this one the Faraday's induction formula right nothing changed at all all right yeah with this one right yeah let's remind ourselves epsilon is equal to minus n and delta phi b divided by delta t right and then phi b is going to be something here right bt at and cosine phi t so it can happen that all those 3 variables which are magnetic flux magnetic field the area of the conductor or the angle of the another can change with time. All right, in that could also be possible in for us. I'm not sure whether you can see whole thing here ยังไปอยู่ไหมครับหน้าจอไปอยู่ไหมเอ่ยผมแชร์แล้วนะเอาไม่ได้แชร์เหรอเอาไม่แชร์หน้าจอไม้ก่อนพูดไปเซิร์ฟเวอร์เลย alright okay we arrive at this page the 2 คนนะครับวันพุธหน้าถ้าใครอยากฟังเรื่องโอ้แต่คุณติดเรียนเนาะคุณติดเรียน605ครับก็เว้นไปเหมือนเดิมครับ alright yeah we arrive here at the formula by Faraday okay the formula by Faraday will give you the amount of the will tell you about the induced EMF. Okay, it has negative value because it acts against the straightforward direction, the forward direction of the magnetic field. Okay, because this one the induced EMF happens due to the change of the flux, okay, which is this factor, and its strength depends also on N, okay, and we will see that those 3 variables, the magnetic flux, the area, the angle between normal of the conductor to the magnetic field, this is the angle, okay, whether it changes with time or not, okay. If it changes with time, usually it's gonna happen in generator, okay, electric generator, which is the next topic after this one, and it can happen that the area can change, okay, but this is a very special scenario, and the case when the magnetic flux changes, this is what we อาจารย์รับผมเข้าด้วยครับว่าริวโอ้ไม่มีหรอว่าริวพิมพ์มา2233ว่าริวเข้ามาแล้วหรือยังว่าริวเข้ามาแล้วนะครับโอเคไหมคาดว่านะครับคาดว่าเข้ามาแล้วนะครับวาริวนะ alright ที่YouTube นะครับมีรวิพลอยู่นะครับ1 คนนะครับเขาชอบส่วนตัวเขานะครับ alright and yeah then we what happened นะครับมันอินเทอร์เน็ตไม่ดีหรือว่าอะไรยังไงผมไม่ทราบนะมันหลุดไปแล้วนั่นจริงด้วยwhat happenedนะครับอยู่ดีก็หลุดนะครับไม่รู้อินเทอร์เน็ตผมไม่ดีหรือว่าอย่างไรนี่กำลัง 5G นะเราเสียบที่นี้นะครับใช้อันนี้ดีกว่า 5G ไม่ค่อยมั่นใจอันนี้ครับของมหาวิทยาลัยผมก็เสียวเหมือนกันครับมหาวิทยาลัยวิ่ง1 กิกนะครับแต่ว่าใช้จริงไม่ค่อยได้เรื่องครับก็ไม่รู้เกิดอะไรขึ้นครับ change it to 3 3 technology alright I hope 604ยังไม่เจ๊งเลยนะครับอันนี้เห็นหมดทุกคนละนะครับจะประมาณนี้นะครับมีคนอยู่จะประมาณนี้นะครับแล้วก็แชร์หน้าจอไม่ทราบว่าไปได้ไหมกำลังจะเริ่มเลยครับดันมีปัญหาอินเทอร์เน็ตนะครับ604เขายังไม่มีเลยครับwhat else all right we go ahead with our story yeah there are 3 variables b a and cosine phi t all right in it can happen that all these 3 variables 3 quantities can change with time whether the magnetic field the area or the angle between the normal vector of that conductor and the magnetic field rightอันนี้แค่ทบทวนครับ and Len says that the induced EMF acts as to oppose the change in flux that produces it. Okay, if you don't understand the word, it's no problem. Let's consider these scenarios. You are gonna understand what Lens said. Okay, ถ้าไม่เข้าใจก็ดูตรงนี้เอาละครับเราจะรู้ว่าสิ่งที่เลนพูดหมายความว่าไงครับ Okay, now let's start the Lens statement. Well, here you have the permanent magnet. You know permanent magnet, right? แม่เหล็กถาวรครับโอเคไหมand in any magnet, whether it's permanent magnet or any other types of magnet, there should be 2 poles, right? The south pole and the north pole. Now let's start with the typical way. Okay, we lay down the north pole toward the plane. Okay, the planar surface of the conductor. This is the loop of the conductor. Okay, in let's see what's going on. At the first state, okay, we leave the permanent magnet like this, and of course, in the typical way at the beginning of this chapter, at the north pole, we are going to have the magnetic field line, right? Going away out of the north pole, right? And this magnetic field line is gonna turn and get into the south pole, okay? And that's in the beginning of this chapter, okay? And that's the first thing, okay? And after that, in the second situation, we will move it toward the conductor, all right? And yeah, that's what a person, that's how a person move the permanent magnets. But let's take a look at the feeling of the conductor. Okay, เรามาดูที่ความรู้สึกของขดลวดบ้างนะว่าเขาเป็นไง Let's take a look at the feeling of the conductor here. At the beginning, the permanent magnet is quite far from him, right? And the magnetic field line is just directed towards him, and yeah, he feel that there is magnetic field with a certain amount, okay, pointing to me, okay, directed to me. And after that, someone move this permanent magnet, and if we are inductor, right, we will find that the magnetic field is stronger when someone move this permanent magnet, right? And he will find that I'm serious, I'm in the pressure because someone leave more magnetic field to me, okay? And let's take a look at the vector statement. Here is the first situation, okay? The conductor receive the magnetic flux with this length, okay, which represent the magnitude of the magnetic flux. And in the second situation, when someone moves this permanent magnet toward him, toward the conductor, he would get stronger magnetic flux, which is this one, okay, delta, which is phi B2, okay, phi B1 represent the magnetic flux for the first scenario, the time T1, and the second scenario, phi B2, okay, represent the flux at time T2. And what happened is in physics, it means that this guy, the conductor, would feel that there is increasing flux to me, okay. You just make the subtraction between the second vector to the first vector, right, which is the typical way in physics, right, because we have to, when we want to say or observe the difference in physics, okay, the typical way is that final state minus initial, right? Okay, initial state, right? And that's also the same thing. Phi B is phi B2, delta phi B is phi B2 minus phi B1. So that's why we get the additional length of the increase in the incoming magnetic flux like this, okay, delta phi B. But the inductor is like a lazy person, okay. He is I don't know, inertia, okay. He's lazy. He doesn't like someone who changes the environment to him, okay. He doesn't like the change with him. So no, someone leave more magnetic flux toward me. He needs to act against this increasing amount of the magnetic flux by generating the magnetic flux in the opposite direction, but with the same amount of this one, okay. It's not exactly the same. You have to convert, you have to divide phi is equal BA, right? You have to divide this one by A, you will get B, okay. B induced, absolute B induced is equal to phi delta phi B by A, okay, the area, the cross-sectional area of this conductor. Okay, all right, this is the relation. We have to generate the magnetic flux in the opposite way to the flux change, okay, when someone moves the permanent magnet towards the conductor, okay. And this is the Lenz statement, okay. He said that the conductor should produce the magnetic flux, okay, to compensate or to get rid of, to remove the increasing amount of magnetic field, okay. If the permanent magnet stay like this all the time, nothing is gonna happen at all right. But if someone move this permanent magnet toward the conductor will be unhappy and he will act against that increasing amount of the magnetic flux, okay, by generating this B field, okay. And in order to have B field, okay, the conductor doesn't have any energy at all, okay. He has to generate the energy itself, okay, in order to get this one, okay. And then in order to have the magnetic flux in this direction, okay, to act against the increasing amount of flux change, he has to generate the current, and the direction of the generated current should follow the right hand, okay. You leave your thumb direction to this one, okay. Your thumb direction นิ้วโป้งนะครับโอเคไหมมือขวาคุณนะครับ your right hand, okay, the thumb on your right hand, lay your thumb on the right hand according to this vector. You will get the direction from your 4 remaining fingers, okay. You have 4 remaining fingers, right, apart from the thumb one, and then you have other remaining 4 fingers, and the 4 remaining fingers will tell you the direction of the current that should be, okay, because usually if we have the current, we will be able to find the magnetic field too, okay, by using the right hand. It's in the same, in a similar way, if we want to find the current direction from the magnetic field, we should apply also the right hand, and your 4 remaining fingers will represent your 4 remaining fingers will represent the current, okay, when you lay your thumb, okay, as direction of the induced B magnetic flux. Okay, that's the situation when we move the North Pole to the conductor. Now let's consider the situation when we move the South Pole of the permanent magnet toward the conductor, like this. Okay, and you know that in the permanent magnet or any kind of magnet, the North Pole is the place where the magnetic field line start, okay, to go out, right? But on the other hand, in the south pole of any magnet, whether it's permanent magnet or electromagnet, okay, the south pole is the place where the magnetic field lines try to get into, okay, the magnetic field lines try to get into the south pole, and it's not the main thing for us. The main person is the conductor here, okay. The conductor will feel that there is magnetic field line pointing toward the south pole, okay. He would feel that I have magnetic flux pointing upward, okay. That's the feeling from the conductor. But if you move it toward the conductor will feel that I get stronger magnetic field lines, but that points upward, okay. It's opposite to this one. He gets the stronger magnetic flux, but with direction with a downward direction. But here the magnetic field line is pointing upward. All right. And what else? In the first situation, you have 5B1. That's the magnetic flux pointing upward. And when someone moves the permanent magnet to be closer to the conductor, the conductor feel that there is stronger magnetic flux, which is 5B2. And in physics, if we want to see any difference, it's the final state minus the initial one, right? So 5B2 minus 5B1 will be delta 5B, okay? And 5B is the change of the flux, which is what the conductor doesn't like, okay? The conductor doesn't like the change of the flux at all, and he tried to get rid of this amount by generating again the magnetic field, which is pointing in the opposite direction to the flux change, okay, in the opposite way. And its relation can be found easily from this one by using this expression, okay, this relation. The current cannot have this induced magnetic flux, except that he generate the currents, okay, around himself, and the direction of the generated current should follow the right hand. In order to get the magnetic field in this direction, you lay down your thumb, okay, lay down in the same way as the induced magnetic field, and you would get induced current, okay, on the conductor loop. All right, and that's the whole story, all the mechanism that happened in the movement of permanent magnet toward the conductor. Now let's consider the second group when we move the permanent magnet out of or away from the conductor, okay, whether it's north pole on the side, okay, and the south pole close to the conductor, okay, the south pole on the right side, okay, and we will see what happened. ตอนนี้ผมขออนุญาตเข้าห้องน้ำแป๊บนึงครับเดี๋ยวมาหน้านี้ให้จบนะครับ Okay, now let's consider the second type of movement for the permanent magnet. We move the uh, permanent magnet away from to be away from the conductor. Okay, the circular or any shape of loop. What the conductor field is that there is magnetic field lines pointing throughout his surface, right? In the vector that he can feel is phi b1, right? Phi b1 like this. But in the second scenario, someone moves this permanent magnet, this object, away from him, and it means he will get lighter magnetic field. Okay, the strength of the magnetic field is going to be lower. Okay, he get less amount of magnetic field, so the vector representation for that amount should be shorter like this. Okay, phi b2 is shorter than phi b1, and according to the typical way of in physics, okay, a difference could be observed again, okay, by final state, right, minus initial state. Initial state. And we make the subtraction between phi b2 and phi b1. We get the negative value, right? Because this final state is shorter. Okay, final state is shorter than the initial state. So we get something negative. So the negative value means the opposite direction of the vector. Okay, all two vectors are pointing in are directed to the low part, right? So here we have upward vector. Okay, the vector pointing upward, and the magnetic the conductor doesn't like the change of the flux at all, which is pointing upward. He tries to compensate or to make the balance, okay, or to get rid of the increasing amount of flux by generating the magnetic flux pointing downward. And if you lay down your forefinger, your thumb direction, okay, you lay your thumb direction down as direction of be induced, you get the current direction from your 4 remaining fingers, okay, with this one, okay, ใช้กดมือขวานะครับเรานิ้วโป้งชี้ลงตาม b induce นะครับ vector b induce นะครับคุณ4 นิ้วของคุณก็จะแสดงทิศของกระแสที่ได้ผลลัพธ์ครับไม่ว่ากรณีใดก็ช่างโอเคไหมครับจะเหนือเข้าเหนือออกหรือว่าใต้เข้าใต้ออกนะครับขั้วใต้ครับโอเคnow let's consider the second scenario for the second type. Okay, we move the permanent magnets away from to be away from the conductor. So here is the south pole, right? The magnetic field realize that there is magnetic field lines passing through him and pointing upward. Okay, pointing up. And what else? Someone moves these permanent magnets to be away from him. Okay, at the beginning he get quite strong vector, quite strong magnetic field line pointing upward. Okay, phi b1 is quite large, and when someone move it out of him, he will get the magnetic field shorter, okay, lighter, which means shorter vectors. And again, we apply the difference in physics. Final state minus initial. Phi b2 minus phi b1. Okay, the final state is shorter, right? So it's going to be negative value, and the negative value means the opposite direction of that vector. Okay, of those two vectors. This is the flux change. Okay, observed by the conductor. All right, in the conductor is a lazy person. Okay, he doesn't like someone to disturb him. Okay, he tried to get rid of this chain, okay, the flux chain, by generating the magnetic flux. Okay, and in order to get that magnetic flux, he has to let the current flow in any certain direction. And in order to find any certain direction of the current, we should apply the right hand again. Okay, you lay down your thumb, okay, pointing upward, okay, as same as B induce it, and you will get the direction for the current from your 4 remaining fingers like this. okayนะครับต้องลองจินตนาการวางตามนะครับเพราะว่าสวิตช์เป็นกล้องมันก็จะวุ่นวายครับพี่กดชวงวัดมาที่ YouTube ด้วยนะครับเซฟไว้ให้นะครับ and yeah now you understand right how the current generation how the current can be generated in the conductor. There is no battery, there is no power source at all in all these 4 cases. Okay, the current just was just generated himself, okay, in the conductor in order to get the be induced, okay, to act against the flux chain, okay, in all those 4 scenarios. If you have any questions about this 4th situation, just let me know. If not, we go ahead with some figures from other books. Okay, this is taken from another book. Okay, all these 4 figures are taken from one book, and this from another book. Let's say if we don't have the current at all, okay, nothing. If we don't let the current flow in this one, there will be no current. And if there will be no current in this conductor, this is the conductor loop. Okay, it doesn't matter whether we have the conductor loop in rectangular shape like this, or in circular shape, or in any shape. Okay, the important thing is that it should be the closed loop from the conductor. Okay, the closed loop of the conductor. Okay, but if someone disturb this situation by letting the current flowing up, okay, by using any battery or any water source, and in that case there is current flowing upward like this, and from the Ampere's law, okay, we could apply the right hand rules, and the amount of the magnetic field could be found from the Biot-Savart formula, right? B equal mu 0 I divided by 2 pi d or 2 pi r, right? If you are far away, you get weaker amount of magnetic field. Yeah, this conductor just stay quite close to the straight, long straight copper wire here, and that has current flowing too, right? And there would be also magnetic field lines that pointing throughout the surface or the area of this conductor loop, the rectangular conductor loop. And if you are the square, the rectangular conductor loop, you will find that at first there is no magnetic field pointing through me at all. But when someone let the current flow, there are some magnetic field lines pointing into me, okay, into my cross-sectional area. This guy will not be happy at all, okay, because someone disturbed him. Okay, conductor like the peaceful situation. Okay, he doesn't want anybody to disturb him, okay, or to annoy him. And then he would try to generate the current in order to get rid of the increasing amount, okay, the magnetic field is pointing to him in this scenario. He will try to generate the magnetic field in the opposite way and with the same amount. Okay, he will not produce the magnetic field greater than that amount, okay, because it beyond his requirement. Okay, he just want to remove anything that changes his cross-sectional area. And in order to get the induced magnetic field, he has to let the current happen and flow in this direction. Okay, it can't flow in this direction from upper to lower because the magnetic field line is going will point into this plane, right? And it's gonna accumulate this previous magnetic field, okay, from the disturbance. He has to let the current flow in this direction so that there will be induced magnetic field pointing in the opposite way to these magnetic field lines. All right, and yeah, this one should be equal to this one, so that there will be complete constellation. Okay, there will be full removal of the exceeds magnetic field. Okay, and yeah, we apply the right hand, we can get the current direction like this. All right, เดี๋ยวเราอะไรนะ15 20 15 40 ใช่ไหมครับผมต้องปล่อยคุณอีกประมาณ34 นาทีครับ as the here is taken from another book, but it's quite close to all those 4 situations, right? That is south pole of the permanent magnet. That is north pole of the permanent magnet. South pole is the place where the magnetic field lines will try to get into, right? And north pole is the place where the magnetic field line start to get out, right? And yeah, it's not the important thing. The conductor is the main person that we have to take care. He will realize that, he will understand that there is magnetic field lines pointing through his surface like this, okay, and that's the first situation. But if someone move this magnetic field line with the velocity vector v towards the surface of this conductor, this conductor will find that I get stronger magnetic field line, someone disturb me, okay, and he will find that he doesn't like the stronger magnetic field line, okay, because someone moved the permanent magnet to be close to him. And after that, he will try to get rid of, to make the cancellation of the excess magnetic flux, okay, by generating the magnetic field in the opposite direction to this one, okay. If you move this one to the conductor, then there will be more magnetic flux from left to right, and he has to reduce this amount, okay, to be in the same level as before. So he will try to generate the magnetic field in the opposite direction from right to left, okay, and he cannot produce it himself, okay. He has to generate the currents around him, okay, by using the right hand rule, the thumb direction laying down here horizontally, and your all 4 remaining finger will represent the current that should flow, okay, and that's the idea. All right. Yeah, that's what happened. Okay, I forgot to mention. N can be considered as the north pole of this magnetic field generation, okay, induction. And on the right side, we could imagine that this is the south pole, because in the south pole we have the south pole is the place where we get the magnetic field line getting into, right? And north pole is the place where we have magnetic field line getting out of, or start to get out, right? What happened? Internet, it's over or what? Fault fine. Internet maybe. Sorry. โอเคครับอีกเครื่องนึงครับอินเทอร์เน็ตมหาวิทยาลัยครับใช้ได้ไม่นานครับใช้มีเวลาจำกัดดีไม่ซูมไม่เตะออกครับไม่คลิกก็ผมเอาครับอินเทอร์เน็ตขาดโอเคthat's the scenario. And let's consider another case when we have electromagnet. Okay, electromagnet is a little bit different from permanent magnet. Okay, permanent magnet ก็คือแม่เหล็กถาวรครับ electromagnet ก็คือแม่เหล็กที่เกิดจากไฟฟ้าโอเคไหมครับมันเป็น it's not permanent magnet, it's temporary magnets. Okay, and its source is electricity, right? You have battery, and you put the energy from the battery, you let the current flow from the plus side, plus polarity of the battery to the conductor, and you let the current flow from the another end of the conductor to the left, to the negative side of the battery. Okay, and that's called electromagnet. Okay, unlike permanent magnet is not complicated. Okay, it's a special behavior of metal. Okay, that has an equal amount of electrons in some orbits. All right, and the solenoid has been wired around a core. Okay, this core is of the cylindrical shape. Okay, the core is cylindrical, and when you open the switch, okay, there will be no current movement, right? There is no current movement because this switch is open, and when there is no current, there will be no magnetic field also in the core. Okay, and there will be no magnetic field lines passing through the surface, the inner surface of that conductor, of this conductor, right? Yeah. And let's consider the second situation when you close the switch. Okay, the switch is closed, and the circuit is fully connected, and the current will start to flow from the positive side polarity of the battery and turning around according to the solenoid shape. Okay, and like this, and the current will flow like this. Okay, to the minus polarity, the negative polarity of the battery. All right. But that's the whole story about current movement inside the solenoid. It's not the main thing. The main thing is there will be magnetic flux. Okay, and if you apply your right hand, okay, according to the direction of current movement, you will get you lay your forefinger as same as the direction of the current movement in the solenoid. You will get the thumb direction as the magnetic field direction. Okay, which is the magnetic field pointing into the core. Okay, like this. มันไม่เป็นอย่างนี้เสมอไปนะขึ้นกับทิศทางการพันขดลวดคุณนะโอเคไหมครับแต่เขาพันอย่างเงี้ยก็คือเส้นลวดมันเข้าไม่ใช่เส้นสนามแม่เหล็กมันเข้าแกนครับ so the conductor will realize that will feel that he will feel that there is magnetic field pointing to him, right? In does he like? He will not like at all. Okay, because someone disturbed him when we turn on the switch. He has to in this scenario, we will not talk about the third figure yet. Okay, let's completely consider the second figure. When there is current move from the right to the left like this, he doesn't like this situation because someone tries to disturb him. He will try to generate magnetic field in the opposite way. Okay, in the opposite way, and in order to get the magnetic field in the opposite way, we will apply the right hand. Okay, lay down our thumb direction of your right hand in this direction. Okay, towards the opposite direction to the magnetic field. Your 4 remaining fingers will represent the current flowing inside the conductor. Okay, and that's the situation when we close switch. Okay, when you let the time goes by, the conductor will be able to accept the dense, okay, the dense magnetic field. Okay, and if you now we move to the figure number 3. If we open the switch, okay, before that he get an amount of magnetic field, right? And when we open the switch, there will be no current move at all in this one, and there will be no magnetic field lines. And this guy again, he doesn't like that situation when someone disturb him. Okay, before that he get a large amount of magnetic field lines, and after that there is no magnetic field lines. He has to generate the magnetic field